Okay, let's look at problem 621. It's a ballistic, tracking the ballistic trajectory or something. The aerospace engineers sometimes compute the trajectories of projectiles, such as rockets. Well, a simpler version, a related problem, deals with the trajectory of a thrown ball. So a trajectory of a thrown ball by a right fielder is defined like this by this equation. Y is all this stuff. Now all the knots, the theta knot, V naught, theta naught, Y naught, those are the initial conditions. Okay, so find the appropriate initial angle theta naught if V naught is 30, so it gets released from his hand at 30 meters per second, and the distance to the catcher is 90 meters. Assume that the throw leaves the right fielder's hand at an elevation of 1.8 meters and the catcher receives it at 1 meter. Okay, so there's a lot going on there, so let's think about it just a second. Basically what it's saying is this person is throwing it a total of 90 meters. He's throwing it from 1.8 meters and the catcher is catching it at 1 meter. So what that means on this little graph is that, this initial condition right here is going to be 1.8 in the Y direction, and it's going to come up here for some unknown distance, and in theory it's going to go exactly 90 meters and it's going to land right at 1 meter, where it's going to be after 90 meters in the X direction. The Y value should be 1 meter, which is where the pitcher or the catcher catches it. Okay, so we need to solve it graphically, and then using a root solving algorithm, and then using the built-in F0. Okay, so let's go through and do this. So I'm gonna start. Let's start with a nice clean slate. Okay, so let's go ahead and start to define the parts we need. We're going to need G is 9.81 meters per second, right? V naught is 30 meters per second. Y naught is 1.8 meters. Okay, so I don't know. What I'm trying to find is theta naught, right? So this equation is kind of, those are constants. X tends to be the variable, so it's kind of, the idea is that you'd have, for some X, here's Y. But what we want to do is say, hey, I'm going to rewrite this and I'm going to solve for theta naught. But at first, let's just kind of look at it and see what it looks like. So I can say Y is equal to at X tangent of theta naught times X minus G over parentheses 2 times V naught squared times cosine of theta naught squared. All that, this should not be there. There we go. All that times X squared plus Y naught. Okay, and I don't have a sense of what theta should be. We need to kind of figure out theta. So let's just plot this. Let's go ahead and do f plot of Y, and we'll go from, say, since it's supposed to go 90 meters, let's go from 0 to 100 meters. So give a little bit of extra space, kind of see how that turns out for us, right? And I like to turn on the grid. Okay, and there we go. Okay, that should give us a sense. Now, the problem is I'm going to run this and I get an error, and the error is going to get mad at me because it's going to recognize that there's missing this theta naught, right? Because I haven't defined that. And I'm just going to take a guess. So let's just, for giggles, let's say theta naught is equal to 20. So I can just kind of get a ballpark sense of what's a reasonable value for theta naught. So let's run that. Okay. Now, first off, that's a lovely plot, but let's look at this. It says warning function behaves unexpectedly on array inputs. So this is a warning, and it's okay, but please don't ignore the warnings. And what that means is basically I need to do a dot operator here, because the way fplot likes to work is it likes to kind of give it an array instead of go one at a time. Okay, so if he releases it at 20 degrees, then it goes out and it crosses 0 at like 70. So it hits the ground 70 meters away is basically what this is saying, right? So hey, what happens if we bump this up to 30 degrees? Now, so the other one was a lie. I forgot to do something. These need to be tangent D and cosine D, because I'm putting it in degrees, not in radians. So actually, let's go back to 20. Did that just happen to work out pretty similar? Yeah, it's pretty similar. So if you release at 20 degrees, you get out to, where is that, around 63 meters, and then it hits the ground. So if you bump that up to 30 degrees, Then now we're getting out a little further, right? Somewhere around 80 some odd meters. And we need to get out to 90 meters. So if we get out to 40. So, okay, now we're at. So now it's at 90 meters. And I keep on saying hits the ground, but in reality we want it to be 1 at 90 meters. So the answer is going to be a little bit less than 40. So somewhere on, so we have that idea. But we don't want to have to keep on going through, well, what about 35, right? This is a very inefficient way. It kind of gives you a ballpark, and it's not an unreasonable thing to do for a first pass to be like, okay, roughly what should we be, right? But it's not going to work. So what do we do? So solving it graphically. This is not really this graphical solution. This is kind of giving us a ballpark idea of where to start looking, but what are we really doing? This right here is, for those in my class, I know this is what I'm going to consider a white elephant, right? This saying we are good at finding zeros. The problem is we're not looking for it to be 0. We're looking for when this equation, when you set x equal to 90, y should equal to 1. And so the problem is that's not our strength. We don't know how to find something equal to 1. We know how to find something when it's equal to 0. So we need to strangle this white elephant and turn it purple. So how do we do that? So let's make a new plot, or a new function. I'm going to say, and I'm just going to say my function is equal to at, and in this case, we're going to look at for theta naught, right? Because that's what we're looking for, at theta naught. And so I'm going to rewrite this whole function, really it's this function over here, right? I'm going to rewrite this function, but I'm going to put this y on this side. And so it's going to be tangent, and I'm going to go with tan d of theta naught times x minus g over, and I'm just going to actually gratuitously copy all this. Let's make life easier. Okay. Oops, copied a little too much. Okay, so g over all that, but then minus y, right? Because we're going to take this y and we're going to put it on this side of the equation, so minus y. Okay, so lovely, but there's a few things that I need now, because now this is a function of theta naught, so which means this and this are what I'm going to send into it, right? So now I need to define some things. X, in this case, it was a range from 0 to 100, right? When we plotted it right here, we were down from 0 to 100. But now x is 90. That comes from this right here. When x is equal to 90, that's what we're looking for. And when x is equal to 90, y is equal to 1. Because that's what it's saying, is that the catcher is receiving it at 1 meters off the ground at 90 meters away. Okay, so now I could do an f plot on this. And actually, maybe that's the thing to do. Let's go ahead and create a new figure. And we're going to go f plot of function. Now, we kind of figured out that it should be somewhere between 30 and 40 degrees. So let's just do that. Let's go from like 20 to 40 degrees. Okay, so let's run that. And there we go. So in this case, we're looking for where this function equals 0, because where this whole thing is equal to 0, then when we subtracted this y over here, this is the answer that we're looking for. So the answer is going to be really close to, what do we have, like 37.8-ish, right? So this is kind of the graphical solution right here. So 37.95, you can go as close as you want, 959, okay? So we'll even put a little comment here. Graphical theta, I can spell it, naught is equal to 37.959. So we decided 959. Yeah, there we go. Okay. Lovely. That's lovely. That's all good. Hopefully you can recognize that that's maybe not like really practical for a lot of things, right? So that tells us a ballpark idea. So what do we do next? Well, now we're gonna do, that's part A. Let's implement a root solving function. Now, to be fair, I wrote the functions, but they're not here. So let's just write an algorithm real quick to do the root solving. And this is a good example of when we don't want to have to do the Newton-Raphson. Newton-Raphson is obviously a great function, it works well, but to take the derivative of this looks unfun to me. And so instead, let's just do the good old bisection method. So I'm going to go So I'm going to say for I equals 1 to a whole bunch, right? And I'm going to say XR is equal to 1/2 of X lower plus X upper. And I'm going to say if function, now function at XR times function of times XL. I arbitrarily picked XL, and if that's less than 0, so I always have to think through this. I just randomly pick the middle point and the left point, the lower point. So if those two are, if it's less than 0, that means answer is on that side. So if the answer is on that side, then therefore X upper is equal to XR, else X lower is equal to XR. And we have to go through and do something. We're going to have to set up an XL. So since we plotted this from 20 to 40, sure, let's go with that 20, and X upper is equal to 40. So if I run that, I get an error. Oh, because you're not allowed to do that. You have to have multiple times. Run that. And I still get an error. So what mistake did I make? F is a function. Did I call it F? I did function here, but I forgot to rename it there. Function. And since I did this, let's go through and let's real quick look at XR. See what XR actually gives us. Boom, run that. And hey, look, it's the same answer, 37.959. Congratulations to us. Okay, so this is very finely accurate but extremely inefficient implementation of the bisection method, right? Because I just did 100,000. I did 100,000 iterations. I probably only need like 20, right? But how many do I need? I don't know in advance. So let's go through and do this. Let's say ES is equal to, and I think it's given here, right? So we need to have at least 3 sig figs. So I'm going to say, actually I'm going to do sig fig is equal to 3. So therefore ES is equal to 0.5 times 10 to the minus sig fig, right? I'm going to set EA is equal to 999. That's my little flag to keep it from going. Because then, let's rewrite this. I'm going to say while the absolute value of EA is greater than ES. So as long as my error is big, go through and calculate this, right? And so the rest of it should be good to go. But I need to calculate EA every time through. And so the way I'm going to do it for ease, there's actually more elegant ways to do it with the bisection method, and you can see it in the other videos. But I'm going to say XR old is equal to XR, right? So what am I doing? I'm going to grab this before I make any changes, call it XR old. I'm going to make a change, and then I'm going to turn around and say EA is equal to XR minus XR old divided by XR, right? And then I'm going to decide whether I update XU or XL and carry on. Okay, the one problem with this, when I run it, it's going to give me an error, because the first time through, it's going to yell at me and say, hey, I don't know what XR is, right? So this first pass through here, the first time I try to do this, I haven't yet defined XR. So the way I get around that is I'm going to say XR is equal to XU, or XL, L, I don't know, something, anything. It doesn't really matter as long as it doesn't end up being exactly this value, because you don't want it to trip. Again, this whole thing is just to make it the first time through. You just don't want it to kick out and run. Okay, now I should be able to run this, boom, and there I get a lovely answer, 37.59. I don't know how many iterations it took. I actually genuinely have no idea. So let's go then. Since I'm not using an index in here, I have to make one up. So I'm going to say n is equal to 0, right? And in here, this is just for counting sake, n is equal to n plus 1. And then here, how many iterations? Boom, run that. And it took 11 iterations, so which is significantly fewer than 100,000. So there we go. We did, now to be fair, we didn't use an existing function that we wrote. I'll make this nice and big. We created the algorithm for the bisection. So we can put a little plot here. Bisection algorithm. So we created a bisection method and solved this function. So notice not this function, right? So we didn't solve this function right here. We put this y over on this side and solved that function, knowing that at x equals 90, y equals 1. And that's kind of the, I don't know, the trick to it. That's the challenge. Again, it's a white elephant problem. We got to strangle that white elephant. We are really good at having all sorts of different ways to solve for zeros. But when it's not solving for a 0, we got to make it look like it's a solve for 0 problem. So there you go. And the last part of the problem, to be fair, this is part C. So I guess this is part B. The last part of the problem is using F0. So F0 is pretty straightforward. We're just going to do an F0 of the function and our initial guess. In this case, I'm just hit 0, why not? And run that and see what we get. And F0 also gives me the same answer. Now, how come I could take such a horrible guess? Well, because quite frankly, the plot of this is really well behaved. I mean, it would make even more sense to say, hey, let's start at like 30, and we're just going to turn around and get the exact same answer. So as long as it's well behaved, it should behave. Well, as long as it's well behaved, it should behave well. There's the brilliant thought of the day. Anyways, so there you go. That is this problem, right? So again, part A, we do the ballistic, but again, this whole thing is a ballistic. Part A, we do it graphically. But the first graphical, this first plot is lovely. It does it. Actually, now that we've done all that, let's plug in what theta naught is. We know the value, 37.959. So I'm just going to plug that in here, 37.959. So I'm going to run this, and just for giggles, let's do this. I'm going to plot from 0 to 100, and I'm going to plot 1, 1. So what I'm doing is I'm plotting just a black straight line at a height of 1 across the whole thing. And the point is that with this angle at 90, this function should cross at that point. So let's run that. Boom. Okay, so there's get rid of that one and look here. I don't know why it does that. Yeah, we'll make it nice and big. So we start at 1.8 meters, we come up way up here, and then we cross right at, look at that, right at 1 meter at 90. At 90 meters downrange, we're exactly 1 meter high. Now, kind of under the unimportant category, let's play with this just for a second. Let's do this. Let's do a X label. This is X distance in meters. Y label Y height. Well, I'm just going to put height in meters. And title is this is the ballistic throw. Okay, so there's one other thing that we could do that's kind of, so run that. Move this. I'm just going to close this. So there we go. There's the nice little thing. The one thing that's a little bit misleading is that, man, you're just throwing this way up in the air. Something that you can do, which is kind of a convenient thing to look at, is just this function called axis equal. And what it does is it makes the steps in the x equal to the steps in the y. So if I run that, all of a sudden that is more true to what's actually happening. So it's, you know, if it's the right thing to do, who knows? It depends on what you're doing. But that's, to me, sometimes that's a really convenient way to do it. It's because otherwise it can be really misleading thinking that you're throwing it straight. Why is he throwing it straight up in the air? He's really not. That's the angle. So now that is that 37.59 degrees or whatever it is. Okay, there you go. Best of luck, and we'll let it go.